Talk about the first one. Somebody tell me your logic for the second one, your story. How did you determine it? How sure are you of the product? And what happened? What do you think? Talk us through. You want to? Yeah, go ahead.
Well, there's a fifth board, and that looked like a tertiary. So then that's what I picked. So then I just drew it as a cyclohexane, so I
Okay.
see it better.
Right.
And I drew. This is where I kind of got confused. So I just drew what I thought it would look like. What would be the molecules on it. All right. The first cyclohexane I drew has a double bond from the top point, right there, and then CH3 hanging off of that. The other one I drew has the double bond in the longer part. So I didn't draw it there. So maybe I should have. That's probably the same thing now that I think about it. But then the other one I drew to do both the E1 and or SN1, the OK hanging off like up there, and then the CH3 hanging off there.
Like that?
Yeah, and then the CH3 on that.
Okay. What do you think about that? Do you have any thoughts, opinions? Do you see similar things, different things? What do you think?
I don't know. It's like
Any other ideas? Any thoughts? No one has anything to say about this? I saw some various things written down. How did what you write compared to this? Did you tell everybody that if they disagreed with you, you'd punch them later? Or something?
I told them I am not going to share chocolate.
Oh, okay. Well, then maybe I shouldn't disagree with you either. Just say that it's correct. Well, I was with you for a little while there. Certainly, so I think your logic about seeing this as a tertiary carbon and then seeing this as a large, bulky base is correct. And that would lead to a preferred elimination product, which would be one of the two things that you drew there. Those would in fact be the same thing as you mentioned as we were drawing that. So I'm going to actually delete this one because there is another product which is this double bond here, making the double bond out that way. And then this, a sort of a substitution product would not happen here. Remember that we're looking for, what does it say here? What reaction type and what product would you expect to predominate? So yeah, you may see some minor products of some of the other mechanisms, but there's going to be one major correct mechanism and then other things that you probably don't need to include. The other issue here is that the nucleophile in this case, remember potassium is a metal, so that's going to be a metal ion all by itself. And the rest of this thing is going to look like that. So even if it were to substitute, it would substitute from there, not with the potassium. So let's look at this one. And in this case, I think we could be pretty confident that there would be really no substitution because being inside a ring like this would be very, very crowded. And a large base like that is not likely to be able to fit in underneath there to substitute that bromine off. So between those two, which do you think is the more likely product here? Yeah, the first one is a little bit more stable, although in this case, there is an advantage that this one has, which is that those hydrogens are farther outside the ring. So they may be a little less crowded, and a really big bulky base may be able to pick that hydrogen off more easily than one of these inside the ring. So you may see more of this one, you may see more of this one. I'm not totally sure where I'd go with that. I think we'd have to do that experiment and try to figure it out that way. And you'll also see that for many, I don't know about these in particular, but even on exams, I'm not always going to write them as totally clear cut. It'll only be this product. Sometimes it could be some possibilities, and I'll usually ask you to explain your choice. And so even if you don't get the one, if you get one of them or the other one, as long as you've justified it properly, you get the credit for it. Right? It's about thinking about these things and making a scientific argument one way or the other. All right, so what's your argument for the next one? Yeah.
Yes, acetone, which I think is a product.
Right.
And then
Be careful though, because sometimes that can trick us. There are things that are more important than the solvent. So what do we need to look at first before we check out the solvent?
we see if it's tertiary.
Right. So in this case, it is. Yeah. So with that, and with the strong nucleophile, then that aprotic solvent becomes important. But just remember that something like this could also be in an aprotic solvent, and it would be the elimination product still. All right, go on. So yes, you're correct. Okay. Yeah. So that's going to be SN2, which tells us that we have that inverted stereochemical configuration because the SH has to come in from behind to displace the bromine. And then we would expect really only one product here. There's not other possibilities. SH is not a strong enough base for an elimination reaction to compete here. And the aprotic solvent tells us that it's unlikely to see SN1 or E1. So that's really the best choice here.
What makes it unlikely for an elimination?
The base not being strong enough. If that were NaOH, we might say maybe there could be some elimination, especially if there were a higher temperature. All right, what about this next one? Okay, Nicole's next. They just sold you out. Go ahead. What did you think for this one? What made you think SN2? Mm-hmm. Yeah. So you think SN2 here, which I think is reasonable. So what would the product be if it's an SN2 reaction? Okay. So that's going to be our SN2 product. So what else might happen here? You went with E2? Why E2? Right, so there could be some E2 product here, which might be, there's actually really a couple possibilities for E2. So you could have this one. You could also have the E, right? And this as well. So these are all examples of E2 products. And that could be a possibility as well. I would potentially question the E2. So I think SN2, I could see an argument for either way here. All right, so this is another one that could be, so these would be the major product. Yeah, so how would I argue this? I could see an argument either way. So with SN2, that's kind of your default position. It's a secondary carbon. It's not terribly crowded there, right? And methoxide is not a very large base. So it's actually not bulky. So, but it is basic. It is strongly basic. So the fact that it's not that bulky makes me think SN2. But the fact that it's a pretty strong base makes me think E2. So that would be kind of the argument there.
Strong base, weak, or strong base, not bulky.
It probably favors SN2 for a secondary carbon. So I would probably favor the SN2 here, but I would certainly understand an argument for the E2 and would probably expect to see both things, both products in this case. Depends on how well you back it up. If it were just simply a question of like fill in the blank of the best product, then you would get it right, I would say, with either product. Yeah. Kind of depends on. I would try to be explicit about that. Meaning like clear, not like I put a bunch of swearing in the question, but I would try to be clear about what kind of answer I was looking for. Maybe there should be more profanity in the exams. I feel like it's like coming off of your head as you're taking the exam, so that's kind of enough in the room. All right, next one. What do you think?
It's that table.
Oh yeah, okay, so that's right. We're going straight around now. So you're next. So what do you think for this one?
We participate too much on this side of the room.
We'll let you chew. Go ahead. All right, maybe I'll take this one. So you said SN2?
Yeah.
Right.
And then acetone is also
Mm-hmm.
and then also it's a secondary.
Mm-hmm.
So that's yeah. And then so I replaced the ER with OE.
Okay. And that's what you got. So yeah, I think all that sounds great. What do you think? Is that what you were also thinking? Mostly? Okay. Yeah, so you've got a secondary carbon again. You've got a strong nucleophile, but a small, and it is also a strong base. Sodium hydroxide is a small base, but it's pretty small, very small actually. So the fact that it's cold and that it's in this aprotic solvent tells us likely that we're going to get substitution, SN2 substitution. How do you draw the SN2 substitution product in this case to make sure that the stereochemistry is correct? Well, one thing you could do, I'm not going to say it's cheating, but one thing you could do is you could just redraw this flat like we did up here. Where? Up here. Right. That would be fine. So you can draw this with both of those down and then just switch the bromine one. But if we do want to keep it in the chair conformation, we have to remember that bromine down, that means that the OH is going to come in from the other side. So the bromine is going to end up at that same position. Yes. What did I say? Oh, sorry. Yeah, so the OH is going to end up. So the up at this position is equatorial up. So that's where our OH would be, and that's what the product should look like. Not straight up, because there's not an axial. So it will come in from straight up, but then it will kind of push out to the equatorial position. So you thought you were done with this stuff, but it just keeps coming back.
Wait, did you switch to axial?
Equatorial. So the bromine was axial. The OH came in from that position, but then ends up equatorial because it has to stay up above that ring because it came in from the top side. At that position, yeah.
Then if we would draw it on the flat, it would be
So, well, depending on how you start it. So we usually use the convention of something down gets a dash and something up gets a wedge? Yeah, so that would mean that this is our starting material. And then the product would end up like that. Good so far? Okay. Ready for the next one now?
Can I do the last one?
Sure. Is that okay with you to do the next one then, Carol? Okay. All right, so you can do this one. Okay. So you got this next one then.
Also, I'm going now. Okay. So I thought this was a primary substrate, and I guessed that this is a base.
Okay.
So
Okay. Any issues with that? Concerns? Problems? Did you get anything different? Same kind of thing? Yeah, so same, I think all that sounds good. So you've got a primary substrate, you've got a nucleophile, decent nucleophile, but not a strong base. And even if it were a strong base in this case, there's no possible elimination products. So there's really no other possibilities, and that's because this carbon doesn't have any hydrogens on it. So there are no beta hydrogens because there are no hydrogens coming off of that carbon. So there cannot be elimination here. So you only have substitution. The only tricky thing about this one is recognizing what the nucleophile is. So this is an ionic compound of K plus and N3 minus. So it's that N3 that ends up hooked on here. There's no stereochemical concerns, so yeah. All right, and this last one, what did you think?
I like E2
Okay, why?
because because the heat is favored elimination.
Mm-hmm.
Since aqueous
Sulfuric acid?
yeah. So I like E2.
Okay, why E2 and not E1? What? No, not sure. Anybody else have ideas about this one? This one was tough because it's a little different. Yeah, what kind of a substrate is this then? It is a tertiary substrate. Yeah, so this is going to be E1. And it's kind of an unusual E1, so we're going to go through the mechanism. But that means that our most favored product is probably this elimination product. So how did we know that it was only E1 and not SN1? I mean, yes, it's hot, but there's another reason here also. Anybody know why it's not SN1? The heat, yeah, but also there's no nucleophile here really to speak of. Sulfuric acid is not really a nucleophile. So what's going on in this reaction? Let's take a look at what's happening in this reaction. Actually, yeah. This is the reaction, or this is the same type of reaction that we had in lab on Wednesday, where we start with an alcohol. I drew it a little bit differently, but the same idea. We start with that alcohol, and we have it in hot aqueous sulfuric acid, which is exactly what we did on Wednesday, right? We took an alcohol and we put it in hot aqueous sulfuric acid, right? Heated it up. So we said that this gives us this elimination product, but let's look at the mechanism of how this is happening. This reaction is called a dehydration reaction. What do you think that means?
Taking away.
Yeah, we're losing water. We're getting rid of H2O. So in the course of this reaction, we have lost H2O. Let's look at how that happens. So you mentioned that this was probably an E1 type mechanism, and that's true, but we need one other kind of special step. The issue is this. In an E1 reaction, you need a good leaving group because you need that leaving group to simply leave on its own, forming carbocation, just like SN1. But OH is not a good leaving group. That will leave and become negatively charged, and that's not likely to occur. So instead, anybody know what we do? How do we make that into a good leaving group so it can leave? Ideas? But we add hydrogen to it. So hot aqueous sulfuric acid is another way of saying hydronium ion. Because water is H2O, and then you put in some acid and it becomes H3O+. So the hydronium ion will protonate the alcohol, meaning give a hydrogen to the alcohol. And then you end up with something like this. So now what is that leaving group? Well, now it's a good leaving group, because now if it leaves, it becomes what? What happens if that falls off? What is it? H2O. That's a fairly stable molecule on its own, right? So we lose that to form the carbocation. And then that H2O can grab one of these hydrogens to finish the elimination. So the only thing different about this from the other E1 reactions we've seen is that first step when the OH has to get a hydrogen before it can fall off. So when you have a bad leaving group like that, sometimes you can make it into a good leaving group by giving it a hydrogen. And that's what happens here. Another neat feature of this dehydration reaction is that there is no substitution competition. The reason for that is that if there were to be a substitution here, that is, the H2O comes back and attacks, then it's just going backwards and forming more starting material. You see that? So the substitution does happen, but it just regenerates the starting material again. So how did we then control that to actually form this in lab? What did we do so that we didn't just keep reforming starting material, but we actually made product? What? Yeah, you drained it out. So as the product was formed, it had a lower boiling point, and so it would come up and condense in that special condenser, and then we took it out. And so if you take something out, you push the equilibrium toward that direction, and that allowed the more product to form. If we just let that acid and alcohol boil in something without taking the product out, nothing would really happen. But every time a little bit of product is formed, we take it out, and so we kind of push the equilibrium along that way. We allow the product to form. So that's the dehydration reaction. And that was good. I think that it sounds like you have a pretty decent handle on the competition of these different reactions. How do you feel about it? You'll get there? So just like anything else, this takes practice. This chapter has a great selection of practice problems for you in the back. So there are all kinds of reactions upon reactions upon reactions of doing this. So both doing the substitutions by themselves doing the eliminations by themselves and practicing drawing those products, then putting them all together and deciding which mechanism is going to predominate, and then also using them in a synthetic way, meaning how do we actually build something from something else. And this is where, so this is what we're going to look at next. And this is where it becomes really, I think, fun. You're probably not going to think fun, but maybe, is what we call synthesis. Kind of the goal of a lot of this organic chemistry. Yes, we want to understand these reactions of these molecules, but a main reason that we want to understand it is so we can control it. So we can say, here is a molecule that we want to make. Let's come up with a sequence of steps so that we start with this molecule, we end with this other molecule. All right, so we'll start with something like this. Let's say we have this molecule on the left, this alkyl chloride, and we want to make this molecule on the right. In any number of steps, we want to make that molecule. So we can think about how we might do that, what reagents we might choose to affect that transformation. How would you go about that? How would you start thinking about that? What? What are you adding? So the first thing to do in analyzing a problem like this is, yeah, look at what changes and what you'd have to add to make that change happen. It might just be one thing. It might be a sequence of things, a sequence of steps to make that happen. So let's say we kind of look like this, right? That's the new part. These parts are the same. And the chlorine has changed and become that, is one way we can look at this. Maybe, or maybe it's simpler than that. In this case, I think it's simpler than that. In this case, really all we need to say first is what's different? Well, instead of chlorine, we have this other stuff. So even that language that we use, instead of this, we now have this, tells us substitution is something we're going to start thinking about. Because we have to substitute this for this other thing that was there. So can we do that directly? Can we come up with a nucleophile that looks like this that might be able to substitute for that chlorine? What do you think? Okay. Well, the nice thing about these problems also is we're not really limited by what's really out there, let's say, right? I mean, yeah, there might be some, we could do that. So in this case, right, so we want a nucleophile that looks like this. If we did that and we reacted with this, we would form this, right? And we want to optimize those yields. So we want a reagent that, that does that and that does minimal other stuff. We don't want competition from elimination reactions. So how might we set this up so that we form this completely without too much competing other stuff? What? Yeah, so let's add that as our reagent. So we're going to take this. We need some kind of counter ion. So we're going to put this thing in there. And what about conditions? What about solvent, temperature? What do you think? Yeah, we want to promote SN2. So what kind of solvent, what kind of temperatures promote substitution? Yeah, so we'd want this to be cold. So maybe, I don't know, 0 degrees C. And then what kind of a solvent do you want to use? DMSO, sure, that's a good aprotic solvent. It's kind of a pain to use sometimes, but that's fine for the purposes of this. And then we would expect that that reaction would give us this product that we want. And that seems good, right? So we did it. Now this is what I call paper chemistry. It works on paper. We could very well go into the lab and try to mix these things together and find that we don't get that product at all. Because that happens sometimes, and then we have to think about some other things. We think about conditions and we try some different things. But we're not going to have to encounter that. I like the idea of having labs where you design your own synthesis of what you're going to make, but logistically, they're difficult because everybody always picks, not on purpose, but people tend to pick like really poisonous or dangerous things because they look good on paper and we usually can't do it, and then we have to go back and revise it, so we'll stick to the paper chemistry with that. But that's how you think about a synthesis like that. What is going to make this other thing? So let's take it one more step from there. Because I mean, we don't want this to be too easy, right? So. So check this one out. Here's a synthetic transformation that we want to think about. And this is very different from before. Because there is no reaction that we know that will do that. Right? That's not a substitution reaction. It's not an elimination reaction. It's not an addition reaction. There's no reaction that takes a chlorine on one carbon and turns it into an OH that then moves over a carbon. That's not a thing. So what does that tell us? How are we going to do a synthesis like this? We want to make that molecule from that one. How do we do that if there's no reaction that does that? Yeah, it means we have more than one step. So we have to start thinking about what sequence of reactions might be able to do that. I dropped my water molecule. So the way to think about this, and this is something that is really important even as these syntheses get to the 10s and 20s and 30s of steps, is something called retrosynthetic analysis, which is a fancy word for work backwards. These problems work better if you work backwards. If you look at the product, and then you say to yourself, what makes this kind of product? What is this a result of? It's kind of like, do you ever do mazes? You know, like where you go through the thing? Everybody know what that is? If you work backwards, it usually works a lot better because you don't get tripped up in the different dead ends as much.
Finish the story.
Yeah. It's the same thing here. We're going to start at the end and go back to the beginning. So rather than thinking, hey, we've got this alkyl chloride, how can we turn this into this alcohol? We're going to say, we want this alcohol. What makes alcohols? And go from there. The reason for that is you narrow down the possibilities. If we say, what does that chlorobutane react with? The answer is a whole bunch of stuff, a whole bunch of possible things. But if we say, what type of a molecule can make that particular alcohol? The answer becomes, well, just a couple things. There are just a couple things that make that product from a reaction. So can anybody think about, thinking back now over all the reactions we've learned, what kind of a reaction can make an alcohol product like that?
Like the B2, like the bromine squared and all that.
Yeah, that kind of stuff.
So the bromine squared and all that? Or the NaOH with the thingy on the bottom? NaOH is on the bottom.
Maybe, but in this case, that would make a different alcohol. So that would make, that would make the one that comes off the end, right? But you're on the right track. It's going to be an addition reaction, so something from the last chapter. And there are actually two possible addition reactions that can make this, so we can write them both down. We can either take a molecule like this and react with acid and water, or we can take a molecule like this and react with acid and water. And either one of those will make that product. If you don't remember those conditions, that's definitely something to review because we'll be using all these reactions together as we go on in these types of problems. So we can think either one of those choices would work, but which one gets us closer to the beginning? Why the first one? You're right, actually. That's true. Actually, this one would be then slightly less substituted. But the idea is that this one can be made from this. Does anybody see how we might be able to make this from that? What kind of a reaction is that? That's an elimination. So how can we come up with some reagents that are likely to cause an elimination and make that product happen? Yep. Keeps falling out. Is it over there somewhere? You see it? Is it stuck underneath the thing? I'm not going to move it because I don't want it to unplug and shut everything down. But I'll probably put this down. So what kind of reagents can we put in there to do that kind of an elimination? Heat, but we're going to need more than that. What kind? So this is kind of thinking the other way. We already thought about how do we predict the mechanism. Now we want a particular mechanism. We want E2 reactions. So what makes E2 reactions happen? A strong base, a strong big base, preferably. So maybe OH or maybe something bigger. A really good elimination base. Yeah, something like maybe this KOTBU, right? That big bulky terbutyl base, that thing. That would, because we can pick whatever we want. So why not pick the best elimination base around? I mean, this isn't the best, but this is a good one. And then maybe heat that up too, just to make sure, right? Because we can pick. So we now have a sequence of steps that allows us to synthesize that alcohol, that 2-butanol, from 1-chlorobutane. If we were to write that down, we might actually write this in order up here. So first, we're going to react this with potassium tert-butoxide, heat it up, and then we're going to react it with water and acid to do the addition reaction. So what does this require of you in terms of knowledge to do this? You have to have a good sense of what kinds of products are made by what kinds of reactions. So for instance, alcohols are made by addition reactions with water, addition of water. Halogens, like if we wanted to add Br to something, well maybe we add HBr to an alkene. All that stuff from that last chapter. What is it that forms from what? And then from this chapter, how do we get alkenes? Well, we get alkenes usually through elimination, through dehydrohalogenation or dehydration, these different kinds of elimination reactions. What are the reagents that we use in those reactions? And that will help us to be able to think about these kinds of things. So let's try another one. I'll let you try this one for our remaining time here. All right, so I'll get you started with this. Once again, we see something a little bit unusual. We see something that we don't know a reaction for. There is no reaction that takes an alkyl bromide and sticks a bromine on next to where there already is a bromine. That's not a reaction that we know. So we have to look back at the end and say, well, okay, what do we make this kind of a molecule from? And then go from there. So go back in your notes or your book, whatever you've got. Try to think about what do we make this type of molecule from? Well, that's something you're gonna have to decide. We can maybe think that it's not gonna be just one. It could be 2, 3, 4, who knows? But what? Oh, you're just thinking to yourself, yeah. The reason we know this can't be just one is just that there is no one reaction that just does that. There is no reaction we know is that just adds one bromine to something that already has a bromine on it. So we have to think about some other ideas. How about we put some things together? Yeah. Yeah, so try that. See if that works. Mm-hmm. Yeah, start from there. You got this? It's not a look of certainty in your face. So another tip with these types of things is this is not the kind of thing where you just stare at it and then magically it comes to you. It's the kind of thing where there's trial and error. You have to write some stuff down, play with some reactions, say, well, what would happen if I took this and I added this to it? What would happen if this thing came from that? You got to play with it a little bit.
I don't, I feel like it's a
Let's do that one.
Show.
It was like show this. Wait, actually, I didn't even work on it.
All right, we only have 2 minutes left, so let's go through this. So, anybody come up with anything yet? Okay, can you describe it?
So I thought the first step would be elimination.
Okay,
Get the double bond.
okay.
Double bond. Then I thought it was application of
Okay. Yeah, I think you're right. So that would do it. Nice job. Another way to think about this is, again, thinking backwards. You can think about, where do we get two bromines like this? What can we use that would give us that kind of a product, which is what you came up with, was that we can do that by adding PR2 to an alkene, that type of a reaction. So that's a way that we can do that. Now, in this case, that happens to be right, but there are other cases where maybe that isn't right. Maybe that isn't the best alkene. Maybe that isn't the only way to do that. But the way to solve these is to write it down anyway. Write down the reaction, see what happens, and then if it doesn't work, you go a different way, you pick something else.
I get it. Like, where are you getting that from the first picture?
So from the first picture, we see that we need a product that has bromines on adjacent carbons. And we know that this is a reaction that adds bromines to adjacent carbons. So yeah, you're right. It doesn't mean that we're getting closer, that we're right, but it's something that works in this case.
Yeah,
So now, yeah.
Like, how do you create a double bond?
Right. So that's the next question then, is how do we then look back from that and say, well, where do double bonds come from? Well, we usually make double bonds through elimination reactions. So would it be possible, whoops, I got too many carbons in here. Would it be possible to do an elimination reaction and get this from this? Is this a potential elimination product of this halide? What do you think? I think, yeah, it is. And how do we know that? Because if this is our bromine, then we can make an elimination on the alpha to the beta hydrogens, which are over here. So the elimination product that would form from this is indeed that one, right? You'd make a double bond right here. So we pick our elimination, whatever. So maybe we use sodium hydroxide this time and heat and do our elimination. Yeah.
That structure, is that how it's supposed to be drawn? I'm just confused.
Which one?
The one right below the two rows.
This one?
Yeah, why isn't it like the first one to the double bond?
It is, but the bromine's gone too. So this carbon is this one is this one. Yeah, there wasn't a carbon down there, that was a bromine. I just erased that. I drew it wrong at first.
Thank you.
So that's our complete synthesis now. And as we learn more reactions, we'll have more choices and more things we can do and more steps we can put in here, so we can make more and more complicated things. So we will play with that next week. All right, well, Wednesday, I think, is the synthesis of aspirin lab. We're also, the lab part of that is pretty quick. So we're going to be also talking about NMR, which is an analytical technique, nuclear magnetic resonance, during that class as well. And then we'll be using that instrument. So I will see you Wednesday.